Welcome everybody to the Polkadot Deep Dives. My name is Joran. Along with my colleagues Lana and Cameron, we are going to take a deep dive into runtime benchmarking today. This is a part of a three-part series. Last week, you guys got a little piece of the first piece of that, which was talking about weights. Today, we're going to talk about the benchmarking framework, and then next week is going to be a more in-depth demo. I just wanted to mention that if at any point in time you guys have questions along the way, go ahead and drop them in the chat box and we'll try and answer them as we go. But there will also be a chance for you to ask questions towards the end. Okay, let's get right into it. So the agenda for today, we're going to talk about why we need benchmarking. We're going to take a look at the benchmarking macro, the benchmarking CLI, and understanding the data that benchmarking is actually going to produce for us and how it's useful. And then we're going to take a look at benchmarking in action with a little bit of a look at the code. Okay. Before we get into the meat of it, I just wanted to give you folks a little bit of a recap of the main bits that are going to be important to us from last week's presentation. So you might remember that we have this concept of a weight. And it's not exactly a weight like you would lift at the gym, but it's a computational weight. And so as we know, all our computers are different. We have different processors, different specs, memory specs, and all that sort of thing. And so running one code on a machine might take a different amount of resources or a different amount of time in comparison to another machine. And so we have this weight that kind of is an average estimation of how long it's going to take the average computer to produce process an extrinsic. And we're going to take a look at what that means. And to just give you an idea of what a unit of weight actually means, the 10 to the 12 weight equals a second, or more specifically, 1,000 weight units is equal to 1 nanosecond. All right, what actually needs to be benchmarked? So if you remember from last week, we have this block, and we have a target block time of 6 seconds. But really, we know that some of that time is going to need to be taken up by importing the block and executing the things in it. So we need time to gossip and import these blocks. And so the time we have to actually execute the extrinsics is only really going to be fitting into 2 seconds. And within that 2 seconds, we have this block import overhead that takes up some time. We have this on initialize hook that takes up some time. Then we have all of the extrinsics that want to be processed during that time, and then we have the on finalize hook. So specifically, like all of these things, we need to have an idea of how long it's going to take the average computer to process it. And specifically, we're going to be looking at what the extrinsics weight, the time it's going to take to process an extrinsic. And it's important to know that every extrinsic has like its base kind of weight, but then the inputs to that extrinsic are going to augment how long it's going to take. It might take longer with one input than another input. And so we need to run iterations of those extrinsics with different parameters in order to find out essentially what the worst case scenario is. So basically, we need to set up a framework, configure a framework to give all the possible parameters for an extrinsic, and then run simulations to generate the average, essentially. So why do we benchmark? To get into the nitty gritty of it, basically, if we have repeated calls to an extrinsic that we've underestimated, then we're going to end up in a scenario where block producers are trying to process these blocks, thinking that they can fit it into the allotted time, but if it turns out that it's taking them longer than expected, and we have basically an overweight block, then it's going to create a cascading failure, essentially, where the block, when you're gossiping the blocks, you don't have enough time to import them. And if you end up being the next block producer, then you're trying to process previous blocks before in the slot that you're trying to actually produce blocks. And this is going to end up cascading and causing the chain to halt, which we saw last week. We also want to make sure that we're charging a higher fee for calls with higher complexity. That kind of just makes sense. We want to charge folks accurately for the amount of computation that they're using, so that they're not getting stuff for free, essentially. And we want to be as accurate as possible without discouraging people from using the network. So it's this delicate balance of, we don't want to charge a huge amount to do anything, because then we get into issues where the chain is not usable for the average person paying exorbitant amounts of funds to do simple transactions. So we have to find this balance between them, and we use benchmarking to do that. We also want to reflect the underlying computation and storage needs, so for storage reads and writes, in a way that keeps the network secure, so that every transaction is being paid for, and they're paying a reasonable amount in order to do that. Okay. So this is why we need the benchmarking framework. And so what the benchmarking framework does is it provides a suite of tools that allows you to run benchmarks and get a bunch of data back from those benchmarks, so that you can analyze it and then take actions based on the data that you get back. And so those tools are the benchmarking macros. Right off the bat, we're going to put in the code benchmarking macro, which I'll show you in a second, which outlines what we want to test, and then we're going to run those macros using the command line tool, and that is going to do a bunch of computation in the background using complex maths, linear regression analysis, and then it's going to produce this amazing set of data that we can then plug into our runtime to give everybody an idea of how long it's going to take for to run any given extrinsic. It's worth noting that the benchmarking pipeline is disabled by default, and if you want to enable it, you have to pass in this flag when you're compiling your node. And the reason is the benchmarking runtime is going to be much bigger than your actual runtime. It's going to add in a bunch of bloat that you don't want to actually put into production. So you run this flag to produce your benchmarks, and then you would compile your node in a different way when you're ready for production. But you're going to take the learnings from this benchmarked runtime to influence that your production runtime. All right, this is what a benchmark macro looks like. It has, it's a very, very simple kind of, just benchmark with an exclamation mark. And the body of this is going to take in the extrinsic name that you want to actually test. And then this is actually very similar to writing tests. So you can kind of bring some of those learnings across. You're going to set up your initial state, basically what variables you're going to use, and what the actual blockchain kind of looks like at the time. And then you're going to you want to ensure that you have this correct state, and then you're going to run the actual the tests against it. And then after that, you want to verify that the final state is actually what you would expect. So very similar to running tests, but what is going to be output is a bunch of data that is useful to you afterwards. And then we're going to jump into the benchmarking CLI. So we're going to pass off to Cameron, who's going to take it from here.
Hi, everyone. My name is Cameron. I'm an integrations engineer, and I will be covering some of the topic for the benchmarking CLI. So as Jordan mentioned, the benchmarking CLI, it's a command line interface that gives you some tools and some different options to do benchmarkings on different things from like pallets to like the actual machine that you're running substrate node on. And just generally, it's kind of like a tool that's used to help do any kind of benchmarking that's related to substrate. So from extrinsics to, all the way up to the entire palette that you might have been trying to test. So benchmarking commands are exposed by the substrate node and also can be exposed by substrate clients. And as it's really created with the goal of having a comprehensive suite of benchmarks that help make it more of an accurate sort of experience developing on substrate, so that you can actually have an optimized experience when people are using your chain or calling different extrinsics on the chain. And there's a default sort of benchmark command. It just shows you like a sort of help command. It shows like the different things that you can actually use for benchmarking. Again, that's some of the things I just mentioned, like if you want to see if your machine is actually capable of running a certain chain, or if your extrinsic sort of estimate is accurate as opposed to like what you're actually getting when you're executing it. So that can help you sort of refine it and make it more performant over time. So that's like the gist of what the benchmarking CLI is, but we'll get into some more details as well. So the benchmarking CLI, there's a block command, and this is a substrate benchmarking process. The substrate benchmarking process aims to predict the resource usage of an unexecuted block, and the block CLI command measures how accurate the prediction is compared to the actual resource usage. So that's kind of what I mentioned before. You have an idea of what this particular extrinsic might cost in weight, but you actually are able to measure that using the CLI. So again, it can be used to measure the accuracy of your pallet's benchmarking. And each block is executed multiple times and the results are averaged. So that idea of, you're making sure that you're not getting setting sort of weights that are outliers. You might have sometimes when you run on certain hardware where you get something that's a little higher on weight or something a little lower on weight. So making sure that we take like a reasonable average is sort of how it's set up to give you your results. And we can actually potentially run this here so we can get an example. Let's see here. So if we were to run this here for a block. So here the command is cargo run profile production benchmark block, which is currently what we're looking at. And this would just do tests from block 1 to block 5. This is on a pre-built dev node. And if we were to run this here, let's see. This can take some time. So luckily, I've actually already run this command. And we can see here, so this is an example output. So what you see is for block 1 to 5, we have some results here. And what it's basically doing is it's showing how much of the actual weight was used as opposed to how much the expected weight, how much weight was expected or sort of estimated to be used. So for block 1, you see there's 474,070 of 2,594,000 nanoseconds used. And that's a total of 18.27%. And for going down the line here, so the next block was used 17%, 15.42%, and these ones just a fraction of percent, 0.04%. And so this is just an example, but you can imagine for your own pallets, if you're using this to sort of check to see what your block weight sort of estimate in real time is, as opposed to what you've estimated to be is, you can sort of look to see, hey, if there's room for improvement, and a good target based on documentation is really like you're looking for like around 85% to 100% of the estimated block weight should be like your target to get for these kinds of benchmarks, because that means that you're not too far off from your actual estimated weight, and that means that there's more computation that can happen.
Hey, Cameron, sorry to interrupt. Can you just give us a quick little zoom so we can see a little bit better? Oh, you're
yeah.
done showing that. Sorry.
Oh, okay. A zoom?
Yeah.
Is that better or a little bit more?
a little bit more, and then just like show again what you were showing, like highlight the points.
Okay,
But
cool. Yeah,
people
for sure.
people can look back and pause at this point
Got it.
to see what you were pointing out.
Okay, sorry about that, everyone. So yeah, so I've zoomed in hopefully enough here. Let's see. So as I was saying, this is the output for this command, and this is just an example from running just 5 blocks. You can imagine if you wanted a larger set of data for your particular node or your particular chain, you could control that from with the from flag and the to flag. But yeah, so essentially what we see here is for block one, we have, in this example, it only used 19.73% of its weight, which corresponds to this amount of nanoseconds. But as I was saying, the goal is to sort of get to around 85% to 100% of your estimate. That means that you're actually more closely estimating correctly, how much each call is actually costing to run, and that means that there's more computation, more transactions that can happen within a block, and it just means that your overall chain is more performant because you're not overestimating too much, and you're more close to what your actual cost is for executing certain things on your chain. So yeah, this is an example for the block command on the CLI, but we'll see there are other commands as well for us to take a look at. And again, this is how you would run it. Cargo run for dev node in particular, dash dash profile production, benchmark block, and then you select, from what block to what block. Um, yeah, so this is what this particular command is useful for. And moving forward, there's also a machine command on CLI. So different substrate-based chains can have different hardware requirements. Not every chain is made equal. Some might, require something more performant, or others might, require a little bit less. And the machine CLI command allows you to determine if a piece of hardware fits the requirements for a given chain or not. It measures the performance of the hardware CPU, the memory, and the disk hard drive while it performs intensive tasks. It can be run multiple times to get more reliable results. Again, sort of like the same idea of getting an average that you can actually have something that's a bit more reliable. Um, and if we were to run this command, here, I may have already run this as well. 1 second. For my own machine, yes. So here is what the example output would look like. So you see its category, CPU, memory, and disk. Tells you which function it actually used to benchmark the machine. The score here, the higher score, the better. It shows the minimum that it expects, and then the actual score that you got here. So you can see for my machine, it's well above the minimum for each of these expectations, and it shows the pass percentage here. You can also there's also a tolerance flag. So if you had like a fault tolerance where it was okay for a machine to be 10% off of the minimum or 5% off, you could actually add that in as well. But this is just another tool, benchmarking tool that you can use to gauge whether or not particular hardware is actually capable of running on a particular chain. And again, these are all based on just the dev substrate chain. But you can use that for any chain, your own custom chain or any existing chain. And yeah, that's pretty straightforward. I'd say it's just used to measure how performant the machine is and if it's going to work for running a node on a particular chain. And moving forward, there's also an overhead command. So each time a block or extrinsic is executed, there's a fixed weight that is charged as execution overhead. This was actually shown in one of the previous slides in the beginning, where there's like an overhead for extrinsics and an overhead for blocks, and it's a part of like the entire block um, production cycle. And this is necessary since the weights that are calculated by pallet benchmarks don't account for these particular overheads. The overhead CLI command calculates the weight cost of executing an empty block as well as an empty extrinsic. Even if the extrinsic is just empty, it has a cost, and these represent the minimum weights for any extrinsic and any block, which are typed as the particular type here is called block execution weight. For an empty block, just the cost of any block that's actually executed, and the extrinsic base weight. Its extrinsic base weight is just an extrinsic doesn't have to have any kind of calculations, any kind of cost at all. Just even an empty extrinsic has a base weight. And to calculate that, this is the command you'd run. Again, it's pretty similar to all the other commands. Instead of machine or block, you just pass in overhead, and that would give you what for that particular node, how much an empty block costs to execute, and how much an empty extrinsic costs. And basically, for the empty extrinsic, it basically fills a block with no ops, which are basically equivalent to empty extrinsics, and then it does an average based on how many no ops it actually executed to find out how much that empty base extrinsic actually costs. And then it adds that on to any extrinsic within your particular palette on your chain as necessary costs as well. So those are two sort of different things. There's the actual cost of your extrinsic that you sort of benchmark and that you set or that you estimate, and then there's actually just the chain's native overhead that every extrinsic has to account for as well, or every block has to account for. And I believe there's also an example output of that here. Let's see. Yeah, so here ran this extrinsic, this overhead call to check for extrinsics and the per block execution overhead, if you can see it here. And it's in nanoseconds. And so this does the calculation, and it basically updates the file within the repo to show the block weights file here to show like, hey, this is the actual weight value that has to be accounted for the palette as well when blocks are produced or when extrinsics are called. And so there's the per block execution overhead, and then there's also the per extrinsic execution overhead. Again, this is a tool that you can use to make sure that that's calculated properly, and the correct value is actually being added to each the block and the extrinsics respectively. That is another command, and this is a storage command. So the storage command is a little bit expensive, so we won't actually run this one. But the way it works is the cost of storage for a substrate-based chain depends on the current chain state. As more blocks are actually added to the chain, it can become more expensive to actually read, access, data in the database. So the storage CLI command measures the cost of storage operations based on a particular snapshot of a specified chain state. So you can imagine if your chain is very new, you don't have too many blocks. Maybe it's really cheap to do reads and writes. But if you have like a massive chain and it's been, it does tons of transactions and it's been running for some time, it could be a little bit more expensive to do reads or writes in the database. So I guess the idea is occasionally you would update this to have accurate storage costs for reads and writes for your chain, and then that would keep sort of things accurate as far as what weights you're calculating for the extrinsics that are actually accessible on your particular chain. So as I said, this takes a very long time to actually run. So I won't actually do a little mini demo on this one or show you any output here, but this is very similar. You'd pass the storage command and specify a state version. The state version is actually, if you're doing like a dev substrate node, or it's always going to be 1, and for Polkadot and other nodes like that, it's going to be 0. But there's more documentation on this as well. And lastly, there is a palette CLI command, and the palette CLI command allows you to run benchmarks for a particular palette, and you can specify a few different flags here. Some of them are the chain you want to, which specifies the chain spec that you want to run against. Execution equals WASM to test with WASM execution environment. There's WASM execution compile to always use WASM time. Palette is, which palette you actually want to run benchmarks for. The extrinsic, you can choose which extrinsic within that palette you want to run. Steps here is the number of samples across component ranges that you want, to run for this particular benchmark. How many times you want to repeat, or how many repetitions for the benchmark you want to run. And then you can, also optionally specify an output path or file directory to where you want to store some of the results of this benchmarking. And we should be able to look at this here. This is actually output running for the dev substrate node for running all palettes and all extrinsics. So this has actually been running for some time. But I did run a small example here. Let's see. Extrinsic. Give me 1 second here. I have some output to show here. Let's see. Extrinsics per block. Perhaps I did not run that, but I can actually see about running this here now. Okay, yeah, so looks like that needs to be rebuilt there. But the whole point is it actually just allows you to either specify a specific extrinsic and a specific palette, or you can run all palettes as well. So to run that, you just specify, star or asterisk as the palette and star or asterisk as the extrinsic. If you just want to run similar to how I am doing here, if you just want to run benchmarks for all of them, or you can specify like transfer keep alive as an extrinsic and palette balances as an example. But this is just another way to test to see if your palette or your extrinsic is actually running close to what you estimate it to be. But example output would be like you might get for a transfer allowed depth, for example, maybe it says 37 microseconds, and in the actual code, what you can see here is the weight estimate for transfer allowed depth. And then you can sort of compare the two and see how close you are to the actual estimate for any particular extrinsic here. And that's how like the weights and the benchmarking can come together. You're just really trying to fine tune the weight estimates that you have for your different extrinsics, and like you can actually test that using these CLI commands. So that's really useful and really powerful tool for developers developing substrate in the substrate ecosystem. So yeah, and let's see. So those are the main commands for the benchmarking CLI, and this little chart or example doc here is showing a high level overview of how some of the linear regression sort of analysis happens. So these components, benchmarks have different components to them. They can, different arguments, basically different inputs. And here you can see, an X, Y, and a Z. And for each one of these, it actually gets ran here, and you can actually repeat. And based on the different combinations of those arguments, you can see how they actually plot on these individual graphs. And this is basically an equation where you can see how based on different arguments, the performance of your particular components are actually being measured. So this is high level, but Lana will be able to get into some more detailed examples in her section. So I'll pass it off to her.
Thank you, Cameron. So yeah, let's look a little bit in more detail in what we see when we actually run individual benchmarks per extrinsic. So this is not a demo. A very detailed demo will come next week, and this is just the benchmarking framework in action. So the example that I wanted to look at is a palette that actually our team wrote recently for a parachain. And it's a DID palette. And we wrote the palette, the weights, and the benchmarks. So it's an easy example to explain. So when we want to calculate a weight function per function per extrinsic, so we need to implement a trait called weight info, which takes in the components that Cameron just mentioned. So in the generic image we just saw, we had these XYZ components, and these are actually just the various parameters that various extrinsics accept. But we'll look into it in more detail. So for example, we have extrinsics, create the ID, takes one parameter, and it returns the weight. So this trait is defined usually in the palette source folder together with the lib file and the test file and the weights file. So this is in the weights file. And so we have to implement these weights because we want to reuse this weight info and these functions in the macro above each of our extrinsics in the palette lib file. So we want to be able to actually call the weight info at issuer implementation. But before we can use this magic, we need to get a certain auto-generated weights file for the palette. And where does it actually come from, right? So we need to implement the actual benchmarks. So the reason why I chose this particular extrinsics to start with is because this extrinsic weight isn't affected by input. So even though we do a lot of repetitions per each time when we benchmark this extrinsic and measure its weight, we get slightly different numbers, but there's no number space to build to do linear regression on. Yes, so it's flat, and we'll see that in a second. So there's no input affecting this extrinsic. So where does this auto-generated weight file come from? So wait, where do I have the actual so this is the actual benchmark that we put into the benchmarks macro in the benchmarking file in the palette folder. And essentially here everything is quite similar to just writing a test, and it doesn't have the component varying. So it looks very simple. And after we actually run this benchmark, what we get is an output of an auto-generated weights file for palette DID, and it's going to be called like that. It's going to be palette.did.rs, and it's going to give us some information about where it was run and when, and the different parameters that were passed in the command of the benchmark, and so on. So what we get is actually a function that we can reuse to place here, to place above our extrinsic, and it basically tells us that this is how much time it took to run the extrinsic, plus this is the weight I need to do one read and one write in the storage that was used in the time of running of this extrinsic. So we see that we do a check whether it contains a key, we do an insert, and so all of these things are accounted for. And so how do the results look? So if you run the with the flag to get the trace of the benchmarking, so essentially it shows us the read and write count. So it's as expected, one read, one write. And we actually that was a very long key which I cut off, but essentially if we are interested into looking into the keys, like what actually we are reading in the storage, so this particular key here, its first part is the string DID, the name of the palette, and then the continuation of it is the storage, which in this extrinsics case it was called issuers. So it was the reason I'm mentioning it because I was looking for this code to just verify which keys I was looking at. So just so you know, you need the 2x the 128-bit hash of a string to query the keys, or at least know which keys you see. So you get a time here, 26,000 nanoseconds, and what else is important here? So as we see, we get a bunch of time results, and this is coming from the repeats of the benchmark. So when we say, you know, the steps is the varying of the component, the parameter that we put in, but in this case we don't have any components. That's why it's empty. It's a fixed there is no input. But nevertheless, our extrinsic time varies a little bit. But nevertheless, by the way, after running this individual extrinsic on my machine, I got a slower time, almost 2 times slower than the one that is in the current weights file that, for example, we have. And that's the reason that it was just run on a different machine. So this is just an example that, of course, it changes. And essentially, what else is important here? Yeah, so when we look at the results, yeah, so we get these two analysis. We get the median slope analysis and the minimum squares analysis, and we get a model that says, okay, so roughly it will be about 43,000 milliseconds, and we don't have any additional component here, yeah, simply because, well, it shouldn't be here, yeah, and we see it reflected in this number, and we just add fixed reads, fixed operations to the storage, fixed weights. But what could be more? Yeah, and the results are of course identical. And what happens if we have something that can actually vary? So, for example, if we take an extrinsic that takes in a parameter, which is a vector, and this vector can contain up to 50 elements, and so depending on the length of this vector, yeah, so this is how we benchmark it. Yeah, we take the parameter that can vary, and it can be 1, 2, or 3 parameters or more, and these are the components. And so in our credentials example, so if we look back at the component slide, we see that when we have 3 components, what we do is we do linear regression analysis. First, we fix 2 of the components at their maximum values and benchmark 1. Then we fix the maximum values of another pair and benchmark the middle one. And then we maximize these 2, and then we benchmark these. So we have 3 different slopes. And essentially, yeah, basically the complexity that is introduced by each of these parameters are added into the time, but we have only one. So we have a simple formula which looks like AX plus K, because we have only one chart. But let's look at how actually this chart would be represented. Okay, so yeah, so here we have a model which gives us a base number of 58 for this. Yeah, so this is the command with the 50 steps, with the 50 repetitions of, no, sorry, the 20 repetitions of each benchmark, and the 50 steps. It means that, for example, C goes from 0 to 50 because we do, well, between 0 and 50, we have exactly 50 steps. So we just check everything. And here we have the mean. Why we need the mean? Because we have 20 repetitions per each. Yeah. And the sigma is the mean squared error that we have the distribution of the points around the value, and we do the regression analysis with these points, and essentially we get a certain slope. And with all this magic happening in the background, so here we have one extra read and then see additional reads, and then we have writes, C writes, so depending on the length of the vector. And how does that look in terms of the weight function for, did I not add this slide? That doesn't that doesn't make sense. Okay, then I have to switch to another window. Excuse me. Can I stop sharing for a second? Can I? I can present share screen window. Okay, let's go here. Share. Yeah. All good. Do I need? I can make it a bit bigger. Okay. So, and it is reflected in the revoke credentials weight, which is again auto generated. So it says here auto generated weights, so we see exactly that. Here's our one read, here's our 1 times C reads, and here's our 1 times C writes. And this is the base values that we are adding, which I don't find that always correspond to the when we do many repetitions. Some of the values diverge quite a lot, but again, it depends on your machine, and not every time that you run it, it's the same. Hence all the repetitions. So another thing that is worth pointing out is what is returned in extrinsic. So for example, here, when we do the calculation for revoke credentials, and we have the credentials as a parameter, rather the length of the credentials, because we have it's an extrinsic that receives the credential as input, and it can calculate the weight upfront. So here we have the worst case scenario, in the sense that it will be very close to what we will get in the end. So we don't necessarily need to return the actual weight that was consumed by this extrinsic, but in certain cases we do have to do that. So in other extrinsics, we when we don't know upfront the length or size of what value we'll be working with, in that case, we do need to return the actual weight consumed, because we don't always want to charge what is considered the worst case scenario upfront. So essentially, an extrinsic might not be executed if you don't have enough to pay for the worst case scenario, but you will not pay for the worst case scenario. So this was the information about the about the weight returned, and I think this is roughly it from.
That will conclude our deep dive today with benchmarking. And make sure, if you haven't already checked out the previous, the part 1 to the session, last week we did weights, check that out, because next week we got a nice deep dive coming with more deeper demos of how benchmarking works and all of that fun stuff. All right, but with that, I will be saying goodbye.
Everyone, thanks for joining us.
Thank you for your time.